Okay,
Hello?
now I see the screen. So I will.
Okay,
sorry
Thomas,
for these
excuse me.
technical difficulties, and sorry that I don't speak Chinese. Anyway, good afternoon to everybody, Mr. Chairman, ladies and gentlemen. So please go to the next slide. So you already gave a little introduction from myself. So I am from NplusT, Italy. My company I founded it around 20 years ago. We are working mostly on the non-volatile memory industry. So for companies developing the memories and companies developing storage devices. So we have test systems and data analysis software for the technology development and for NAND characterization. So please go ahead. So my topics is the challenges coming from the ONFI5 and the NVM and the NAND evolution, NAND technology evolution. So what are the challenges related to the storage design? What information, additional information related to standard characterization is required? What are the best characterization strategies, and what are the ideal toolings for doing this characterization? That is what I will speak about. So go to the next slide, please. Okay, so ONFI5. So it was published in mid-2021, and it is a rather important step in the NAND evolution. So it introduces the high-speed interface. It defines up to 2,400 megatransfer per second, the NVDDR3, and it also the low-power LPDDR4. It introduces data inversion, several training procedures. So this is a first challenge. After that, more and more the multi-plane management is included in this standard. And it also introduces low footprint packages, so to making smaller and smaller storage devices. Go ahead, please. From the technology point of view, it's evidently, of course, a lower geometry. We are reaching 100+ layers. The number of dies, LANs, and planes in the same package are increasing. Of course, the program and read times are shorter and shorter. And what we see that another challenge that the I/O and the core currents, and the average and peak currents are really increasing a lot, which is of course normal because of the higher number of cells and the higher I/O speed. Go ahead, please. Yes. So if you want to build a good storage design, of course you have to care about a lot of things. So your goals are to have a good power and signal stability. First challenge. Of course, you want to get the best QoS, performance, and longest lifetime. So the previous speeches were speaking about. So if you want to reach these goals, of course, you have to do a lot of cares and improvements. So you have to design a very good power supply subsystem, the digital interfaces, layout, signal integrity, to implement the good media management firmware with the strategies, NAND management strategies, and of course the error correction, the ECC LDPC word has to be also cared. Of course, you can do it if you have a good knowledge. So you have to understand bit error rates and VT distributions, not only at the beginning of the lifetime, but during the entire lifetime at the various temperatures, getting the power profile, various operations, various conditions, understanding the DQF margin windows. So you need a lot of knowledge. Go ahead, please. I always press that this knowledge has to be based on high quality data. It's not only on data, but high quality data. So the first and most important point is that if you want to understand the NAND and characterize the NAND, you have to do it in a very similar manner as it will operate in the final application. This is one of the reasons that you cannot get from NAND vendors information, because they don't know how you will use their NAND. Other important thing is the temperature dependency. So the lower geometry has a higher temperature dependency, and the temperature impacts very strongly the reliability. So you have to do the characterization at several temperatures. Of course, you have to follow the device aging. During the entire lifetime, the number of cycles, and to generate the endurance retention data, VT shift data, and so on. And because of the critical technology and the high process variation, if you have a low quantity of data, it will be impacted by this variation. So you need to really generate a lot of statistics. Go ahead, please. So let's see a certain specific points. So signal integrity, it is an issue. We are speaking about picoseconds, so the alignment of the signals in picoseconds. The thermal effect also impacts the speed, and the speed impacts the thermal behavior. Of course, the speed impacts also the power supplies. So we always say that you have to do the characterization in a similar way as it will work in the storage device, and it includes also the interface speed. So if you want to run the SSD at a 1.6 gigatransfer per second, this is the speed you need to do the characterization. And of course, higher speed of course saves your time and shortens the time to do the characterization, and you can do more statistics. Go ahead, please. Another point is that we said that the power starts to be challenging due to the high peak currents and the high average currents. You need to generate power data, and here I think it's very important to measure every NAND independently. So if you have a parallel system where one tester measures the current of high number of NANDs, the data quality will be not good. Of course, you can do only one measurement. In that case, the quantity will be not sufficient. So the architecture that every NAND has its own power profile, it's important. And also not only to measure average current, but also to understand peaks and eventually also waveforms. If you have power waveforms, you can also see something about the device operation, which can help you to understand device degradation. Go ahead, please. Another thing, we said that we have many dies, LANs inside one package, and if you can do the parallel characterization of the multiple dies and LANs and planes, this will help you to understand better the device, not only generate more data, but also because also the SSD controller will work in this way. And also, of course, multiple dies parallel will have a higher challenge on the power supplies, which is also important. So go to the next slide, which shows a little table. In this table, you can see a correlation between the number of dies you can test in parallel, in number of planes you can test in parallel at a certain I/O speed. And you see that the higher I/O speed, of course, you can test more dies and more planes together. And for reference, we had a 16 kilobyte page size and 60 microsecond read time. Okay, go ahead, please. Another thing is per socket independent testing. What could be the advantages? If you have a tester per socket architecture, that means that you can do same test with same parameters, like in a parallel system with smaller advantages, but you can do also same test with different parameters, which will increase the quality of the data you generate. You can test asynchronously the devices, so you don't need to put all the devices inside and then start the test, but you can shift them by time, but also it allows to run different tests and also on different devices in the several packages, which in total, this architecture reduces the total characterization time and also gives you a higher visibility and a higher quality results. Go ahead, please. And the next challenge, which is I don't think that we have to abandon, so we have to absolutely to consider that the characterization starts to be very, very complex. So you have hundreds of functions to test and hundreds of configurations to test, develop, validate, and if you don't have an efficient workflow to develop the test programs, this will mean that you will get either a long development time and your manager will be angry, or you can, even worse, you can get bad data which you will discover then the storage device does not work as you expected. Go ahead, please. So in my last sequence will be related how an ideal characterization tool should look like. So we already highlighted the benefits. So the independent per socket architecture means that you can control independently for every NAND package the temperature, the voltage, the test procedures, the start-stop times, which will result in higher data quality and better equipment utilization. Next, please. Of course, the scalability is also important from the small systems which have a few sockets until the bigger systems. So we build now racks with 84 sockets, and also the possibility to cascade and share data between multiple racks. So this helps you to tailor your investment and optimize your investment. And you can really generate on a lot of data. So we measure the 250 gigabyte per second data generation with a single 84 socket rack system. Go ahead. Of course, the edge speed test, which we said it is important. It's not only the interface speed, also the low overhead or the zero overhead during the test pattern generation, the verification and the data compression of the results read out of the NAND. This means that you will have an application-like test. You will be able to understand also the timing margins, and of course you will save test time. Next, please. Also, what we highlighted before, an efficient power profiler, which is that you can measure the current dynamically, so you can capture also waveform per package. And it's also important because, of course, you have measurement noise and you have some other challenges to have an on-the-fly filtering and on-the-fly peak detection. And this will allow you to generate sufficient statistics for optimizing your SSD hardware. And also, it helps you to understand device operation during aging. Next. And of course, and there is also an aspect related to the software. So if you have a good development tool set, which can include a library, function libraries, so you don't need to implement everything from the scratch. You have test program skeletons that you can also only parameterize and put in sequence without writing the whole program. To debug tools like a waveform viewer that you can see what the sequences what you program, how they really look like. So this will allow you to have a faster test development, which is even more important that the results will be more reliable, and of course you will save also engineering effort. Next, please. And of course the scalability, the well-defined roadmap, which helps you to helps you to upgrade the system when it is needed. If the architecture is modular, that means that you don't need to throw away or buy a new system just to upgrade your existing system for higher speeds, for new package types, or eventually for new data and device management functions. So this will optimize your investment and continuously without introducing new learning curves. It will enable you to generate high quality data. Next, please. And this is my roadmap. So we started in 2017 with the 400 megatransfer per second system. In 2018, we doubled the speed. In 2020, we came out with the next generation, which reaches again doubles the speed and 1.6 gigatransfer per second speed, and it introduced the power profiling. This year we created the cascaded 84 socket equipments, and we fully renewed our development tool set. In 2022, we plan to reach the 2.4 gigatransfer per second, which is will be the top of the industry. So introduce the low pitch, low size package management, and also the low temperature. So this is how we see the NAND characterization of the latest technologies from the tooling point of view. And thanks really for your attention, and I appreciate that you gave me this opportunity. Thank you very much.
Okay, thanks, Thomas. Okay, I will change the screen share.
Yes.
Okay. Okay. On behalf of CCF YOCSEF Shanghai, China, we want to express our thanks. We want to say thanks, Thomas, for to work as the presenter for this the special inviter of this forum. Okay, this is an electronic card, and we want to say thank you, Thomas.
Thank you very much.
Okay.
Enjoy the meeting.
Okay.